At the physical level, moving electricity is a loss problem. Every kilometer adds resistance. Every junction introduces instability. In conventional transmission, losses scale quickly with distance. At standard high voltage, moving power more than a few hundred kilometers becomes inefficient and difficult to control. That's why most grids stop there. The constraint isn't generation, it's transmission physics. As current increases, conductors heat. As they heat, resistance climbs. The metal expands physically, and the line begins to sag. Sag reduces ground clearance. Push past thermal limits, and protection systems trip. Distance turns small errors into system failures. This is why long-distance power was historically treated as a risk. Voltage control degrades. Reactive power becomes unstable. Faults propagate instead of isolating. Beyond a certain length, lines stop behaving like conductors and start behaving like antennas. Most grids avoid this region entirely. This system did the opposite. Instead of shortening distance, it attacked the loss equation directly. Voltage was pushed higher, not incrementally, but by orders of magnitude. At ultra-high voltage, current drops. Lower current means less heat. Less heat means lower sag. Lower sag keeps mechanical limits stable. The line stays inside thermal and physical tolerances. This changes what distance means. At these voltages, moving power 1,000 kilometers no longer dominates losses. At 2,000 kilometers, efficiency remains predictable. Transmission stops being the bottleneck. Control becomes the limiting factor instead. But pushing voltage introduces new problems. Insulation breakdown, corona discharge, switching transients. At these levels, mistakes destroy equipment instantly. So the system isn't just larger, it's more precise. Substations are spaced differently, clearances increase, protection thresholds tighten. Power electronics absorb what mechanical systems cannot. Every component is designed for predictable behavior at scale. This is what the grid actually is. Not a collection of lines, but a continental transmission machine, built to operate near physical limits, without crossing them. Once that machine exists, a different set of problems becomes solvable. Once transmission distances exceed a few hundred kilometers, control stops being optional. At continental scale, small instabilities grow quickly. A minor phase imbalance, a delayed response, or a misaligned protection setting can cascade across regions in seconds. This is why most grids avoid operating at this scale. The primary challenge is synchronization. Large interconnected systems must maintain phase alignment within tight tolerances. At 50 Hz, a deviation of even 0.2 Hz triggers protective responses. Generators disconnect. Loads shed automatically. At continental scale, those thresholds are reached faster. Distance amplifies delay. This system addressed the problem at the hardware level. Instead of relying solely on synchronous AC behavior, it segmented the grid. Ultra-long-distance corridors were built using HVDC links. Direct current does not require phase synchronization. It isolates disturbances instead of spreading them. HVDC corridors act as valves. Power flow is set explicitly, not inferred. If instability appears on one side, the link limits transfer automatically. Faults remain contained. AC regions stay synchronized within safe boundaries. This changes failure behavior. In purely AC systems, faults propagate through rigid coupling. In segmented systems, faults hit control limits. The system trips selectively, instead of collapsing globally. Reactive power management is handled the same way. At long distances, voltage collapse is a primary risk. This system distributes static volt-ampere as reactive compensators, synchronous condensers, and power electronics along transmission paths. Voltage is corrected locally before instability travels upstream. Protection logic is standardized. Trip thresholds, response times, fault classification are aligned across regions. This prevents miscoordination between systems. Lines don't fight each other. Control centers operate from a unified state model. Operators don't guess. They see line loading, thermal margins, and stability limits in real time. When limits approach, flows are adjusted before protection triggers. This is what makes scale survivable. Not intelligence, not heroics, but a system designed to fail gradually, instead of catastrophically. At the industrial level, electricity is not a cost problem. It's a continuity problem. Heavy industry does not fail because power is expensive. It fails because power is unstable. Processes like steel making, aluminum smelting, chemical cracking operate inside narrow electrical limits. Voltage excursions above plus or minus 5% accelerate equipment wear. Frequency deviations trigger automatic shutdowns. Restarting these systems can take hours or days. That downtime costs more than electricity itself. Because of this, factories historically clustered near generation. Not for efficiency, but for control. Distance increased fault exposure. Each additional transmission segment added another failure point. Industry optimized for proximity, because the grid could not absorb risk. A coordinated grid changes that equation. When voltage and frequency remain inside tolerance regardless of distance, electrical risk decouples from geography. Factories no longer need dedicated generation or localized reserve margins. They connect to the system instead of defending against it. This directly affects plant design. On-site backup capacity shrinks. Power conditioning equipment can be downsized. Electrical layouts are simplified because stability is provided upstream. Capital costs fall, not because electricity is cheaper, but because redundancy becomes unnecessary. Siting constraints loosen as well. Factories no longer need to sit near coal, near dams, or near coastal fuel access. They can be placed where land is available, where logistics align, and where labor exists. Electricity arrives as a system service, not a local resource. This changes expansion behavior. In fragmented grids, capacity additions trigger grid upgrades. New factories wait for substations, for transmission, for local approvals. In a coordinated grid, expansion is gated by transmission margin. If margin exists, connection proceeds. Lead times compress from years to months. Operational reliability compounds over time. Fewer unplanned shutdowns, less thermal cycling of equipment, longer maintenance intervals. Plants operate closer to design capacity, more consistently. That consistency is what attracts capital. This is the real inversion. Industry no longer asks where energy exists. It asks whether the grid can guarantee behavior. When the answer is yes, location stops being a constraint. At this scale, the limiting factor is no longer physics. It's decision latency. Power flows near the speed of light. Grid decisions do not. Most national grids are fragmented by design. Transmission assets are split across multiple owners. Operating authority is layered. Planning responsibility is regional. That fragmentation introduces delay before electricity ever moves. At the operational level, every major transmission project requires synchronized approval. Land access, environmental review, local permitting, cost allocation. Each step has independent veto power. Approval timelines stretch from 5 years to 15 years before a single conductor is energized. During that time, demand continues to rise. Load forecasts shift. Industrial plans change. By the time infrastructure arrives, it is often sized for conditions that no longer exist. This creates a structural mismatch. Grids are forced to operate closer to thermal limits, with less reserve margin and fewer routing options. Reliability is maintained, but only through conservative operation. Power flows are restricted. Potential capacity stays unused. Coordination compounds the problem. In fragmented systems, cross-regional transfers require negotiation. Dispatch decisions are bounded by jurisdictional agreements. Emergency authority is limited. During stress events, operators prioritize local stability, even if system-wide efficiency suffers. This prevents large-scale optimization. Maintenance exposes the constraint further. In fragmented grids, taking a line offline removes capacity locally. Rerouting is limited by interconnection agreements. Maintenance windows are compressed or deferred entirely. Asset wear accelerates. Long-term reliability declines. These systems are not poorly run. They are operating within governance limits. Limits that prioritize autonomy over coordination. That trade-off stabilizes regions, but caps scale. This is why replication is slow. Not because the design is unknown, but because the system requires alignment across ownership, authority, and planning horizons. For longer than most grids are structured to sustain. Once scale reaches this level, coordination itself becomes infrastructure, and the systems that can maintain it gain operational flexibility that others simply cannot. At this point, the difference between grids is no longer technical. The physics are understood. The hardware exists. The control theory is mature. What separates systems now is not capability, but intent. When electricity can be moved predictably, at continental scale, and governed as a single system, it stops being a background utility. It becomes a strategic layer. Because every modern system rides on electrical behavior. Industry, logistics, data centers, automated manufacturing, all of them assume that electricity behaves within tight limits, all the time. When a grid can guarantee that behavior, it quietly reshapes the economy above it. Factories expand faster, capital commits earlier, supply chains stretch farther without increasing risk. Electricity doesn't just power growth, it sets the speed limit for growth. And once grids reach this level, the advantage compounds. Each expansion reinforces coordination. Each upgrade reduces uncertainty. Each avoided failure builds confidence. Over time, the grid stops reacting to demand and starts shaping it. This is the quiet shift most discussions miss. Electricity is no longer just infrastructure. It is becoming governance. Not in law, but in behavior. Which regions grow? Which industries scale? Which investments feel safe? Those outcomes are increasingly decided by how electricity is coordinated, not how cheaply it is produced. The real divide, then, is not between countries. It's between systems that treat electricity as a commodity and systems that treat it as a platform. One model reacts, the other shapes. And as electrification accelerates, through industry, through automation, through AI-driven infrastructure, that difference becomes decisive. Not overnight, not dramatically, but structurally. Electricity once followed geography, then it followed engineering. Now it follows coordination. And the systems that learn to organize it at scale are quietly redefining what modern power really means.